but is on CO2 emissions and CO2 in the atmosphere on planet Earth. So what we are emitting from the Earth and what is in the atmosphere on Earth. And spoiler alert, it's not pretty, it's not good. Alright, so why does this matter? I think you should all know this. We go to Chwonky, we take natural history, but if you need a little reminder, here is an excerpt from a Columbia paper on this topic. Basically, we're just emitting too much and it's going into our atmosphere and we can't use up the CO2 fast enough, so it's growing. So for CO2 in the atmosphere, I got the data from NOAA, which is the National Oceanic and Atmospheric Association, and it's a really awesome site. They have a ton of data on a lot of different things. But it's important to note that the data is a fraction, defined as the number of molecules of carbon dioxide divided by the number of molecules of dry air. So it's like molecules of carbon divided by molecules of air multiplied by a million, so ppm. And the data before NOAA started collecting is from Big Bang ice cores from the North and South Poles, which we learned about in natural history. That's a photo of on the NOAA website of where they do this, which looks pretty nice. So why do I think this is an exponential function? So the data we have from ice cores and the data from Mauna Loa in Hawaii after 1950 suggests that it's an exponential function because the rate of change keeps going up. The slope at each point keeps getting larger and larger and larger over time. Yeah, that's pretty much that. Oh, and you can see in the slide how it's not, like we don't really have really great data, but then after 1958 we started getting a lot more data that wasn't on my scores. So this is the graph of CO2 in the atmosphere, and the red line is the carbon dioxide data, and the black line is the seasonally corrected data. And I don't know if that means that they just took the average for each year. Oh god, sorry. I assume that's what they did, and then put it into the black line. And I used the mean in each year for my data. So you can see it's a slight exponential, like the end of the last graph that I just showed you. So this is the zoomed in version of the data that I have. You can't really see the equation because it's really small. But it doesn't, if you just looked at this data, you wouldn't think it's exponential. You would just think, oh, it's a straight line. You're stupid, it's linear. So that's my equation. I'm not going to talk about it that much, it's exponential. When you zoom out, it's a lot easier to see. Actually, it's not easier to see because you can't see it, but it goes like that. So it's exponential, and from those, you can see the start of those little points, but then it is exponential. So that's pretty bad news, honestly. It's rising quickly, and it's not good. So that's what's in the atmosphere. So then I wanted to look at emissions. So for the emissions of carbon dioxide, it's a little more challenging to pick a function. I originally worked with the natural log because that's what fit just the zoomed in version of my data, but a lot of things would fit this. So I zoomed out. I'm realizing now I maybe should have drawn this on the board. So I tried an exponential function where, like the carbon dioxide in the atmosphere, it rose really quickly at a really rapid rate of change, or really rapid growth. Yeah, and so the rate of change would keep growing. And for the linear function, which you also can't really see here, it has a constant rate of growth throughout, so the same time it's going by the same thing. It's the same, stays the same. And for the natural log function, the rate of change will never completely level off. It's this one. It's going to grow and grow and grow, and then it'll never completely level off, but it'll keep getting closer and closer to leveling off. So those are kind of the derivative explanations. I didn't actually calculate the derivatives because you can kind of understand basically what's going on. So I'm not sure what will happen with CO2 emission. It's kind of dependent on how long humans are emitting them, how long we last, if there's a max population that will cap off how much we can emit, and obviously the amount of fossil fuels we have left. So there's a lot of factors. So I'm not exactly sure which one is best. I doubt it's linear. It's really hard to have a perfect linear function that goes at the same rate, and we're humans, so we're not really perfect. Okay. And so if the emissions are natural log, then in 2027, when I'm 30 and I will perhaps be having children, we will have 38.57 thousand metric tons of CO2 emitted. And that's 13 years from now, and that's 8,000 metric tons more than we are emitting today, which is really scary. Yeah, that was kind of my conclusion application. And this is my bibliography. Are there any questions? Yes?
Okay, so you say that you're, or like that there's like a certain amount being released into the air, but does it take into account the fact that it's being like reabsorbed by like trees or like other things, or is that just like the straight up?
I think it's just the straight up. I got it from the World Bank data, and I think it was just emissions.
Yeah, cool.
So like how much we're emitting, not how much is being taken back in.
Cool.
And the atmosphere is from the NOAA data, and I can actually figure out how they took that data.
Can you go back to it? Yeah, show us that. That'd be cool.
The what?
The NOAA data,
Yeah.
the graph of, actually, yeah, you know which one.
And I looked online, and it made it seem like there was this one place in Hawaii that's like the best place to take CO2 data. I don't know why, and I don't know if they take it from the air, the water, and the land. I think that's what they do. But I don't know how, if they have like measurers. I'm not really sure how they actually do it. I'm really curious now because it like wasn't flat out on the website.
Yeah, that picture that you put up, the one you said that was beautiful.
Yeah.
The place, that's it.
I just don't know. Yeah, I know
that's on the top of the volcano of Mauna Loa.
Oh, it's a volcano.
Yeah, 14,000 feet. So it's at the top. So they try to get up into the atmosphere. And it shows why, because it's away from most sources of CO2, right? Industrial sources of CO2.
It's the furthest away from me.
Yeah.
So I guess they're trying to get like a base level.
They're trying to get someplace where they're really measuring, in a sense, the homogeneous nature of the atmosphere.
Yeah.
Rather than taking it near somebody's tailpipe. Right?
That would give you a different ratio. Any other questions?
I see you took the mean there, right?
Yeah.
The up and down.
Yeah, that looks really sinusoidal.
Sinusoidal, huh?
Yeah, it looks completely sinusoidal.
Do you know what the period is for that thing?
I think it might be every month is like what they do, but I'm not sure.
So on the scale on the bottom, 1960 to 1970, you see that? Can you do a quick count of how many times it cycles? Can you see that? Just an estimate of how many times it cycles.
So is it every year? Okay. I think that's why.
How many of these happen in there?
The
yeah.
seasons.
Seasonal. So that is the trees sucking it up. So it's actually drawing it down, right? And then when we have winter in the northern hemisphere, there's nothing to suck it down, so the CO2 level goes up. So that springiness is actually due to the natural nature, in a sense, working on that CO2 that we're putting in.
Also,
Really
yeah, Hawaii is on the equator, so if you took it somewhere else, I think that this is like a pretty perfect sign graph because they have nice seasons. But if they took it in Antarctica, it would be probably.
And they're actually, that sensor, you saw the big probe that was up in the sky, that's where they're measuring it. They will, just like the water flow stuff we use, there's a CO2 measuring device that measures how much carbon dioxide there is in the air.
That's really cool.
Yeah.
Thanks, everyone.
Awesome.
Do you want me to send this to you?
Yeah, would you? That's great. I love it.